Hello dear students, welcome to our online learning process. Myself Mrs. Vanita Gaikwad from HPT Arts and RYK Science Junior College. Today we'll discuss magnetic fields due to an electric current, Ampere's law and its applications. We know that the magnetic field at a point on the axis is given by Bz equal to mu 0 I r square divided by twice into bracket z square plus r square raised to 3 by 2. As a special case, the field at the center of the loop is obtained by substituting z equal to 0 in the above equation. So if in the above equation, in the denominator, we substitute 0 instead of z, the equation becomes b0 equal to mu 0 I upon 2r. The same equation we had obtained in the expression for the magnetic field at the center of the current carrying loop. If the coil has n number of turns, then the equation can be written as B equal to mu 0 Ni upon 2R. The magnetic field lines from a circular loop are shown in the picture. What should be the direction of this field? The direction of the field is as per the right hand rule. In this rule, curl the palm of your right hand along the circular wire with the fingers in the direction of current. The stretched right hand thumb then gives the direction of magnetic field. Let us see how a circular loop carrying a current acts as a magnetic dipole. The behavior of the magnetic field due to a circular current loop is very similar to that due to electric field of an electric dipole. At large distance z from the loop along its axis, the equation for Bz is Bz equal to mu 0 I r square upon 2z cube. We know that area of the loop is A equal to pi r square. So substituting A, Bz equal to mu 0 Ia upon 2 pi z cube at z very far from r. The magnetic moment m bar of a circular loop is defined as m bar equal to I a bar, where a bar is a vector of magnitude a and direction perpendicular to a. So above equation becomes Bz equal to mu 0 m upon 2 pi z cube. In equation 2, we have substituted m instead of Ia. Therefore, Bz bar equal to mu 0 upon 4 pi into 2m upon z cube. Note here Bz bar and m bar are in the same direction perpendicular to the plane of loop. Analogously, E bar equal to twice P bar upon 4 pi epsilon 0 Z cube is the electric field at an axial point of an electric dipole. Our next article is Ampere's law. We know that if a distribution of charges is given, one can obtain the electric field. Similarly, the magnetic field produced by a distribution of currents can be obtained. If the distribution of currents has same symmetry, then we can use Ampere's law to find out the magnetic field. That means the Ampere's law is used to find the magnetic fields for the closed loops. The Ampere's law can be derived from Biot-Savart law. The mathematical form for Ampere's law is closed integral over B bar dot ds bar equal to mu 0 I. This sign indicates that the integral is to be evaluated over a closed loop, which is called as Amperian loop. Figure shows the cross sections of four long straight wires carrying currents I1, I2, I3, I4 into or out of the plane of the paper. An Amperian loop is drawn to encircle three of the current wires and not the fourth one. In the chapter electrostatics, you have studied that to find the electric intensity at the point out of the charged body, you have to consider a Gaussian surface. Similarly, here we have to assume closed Amperian loop to find the integral. Now let us come to the diagram. The direction of current is perpendicular to the plane of paper. B bar is also in the plane of paper even if its direction is unknown. The length element on the Amperian loop is dl bar. Therefore, we can write the dot product of magnetic field vector and length element as b bar dot dl bar equal to b dl cos theta. From the definition or statement of Ampere's law, we can write the closed integral over b bar dot dl bar equal to closed integral over b cos theta dl equal to mu 0 I. To mark the currents with positive sign or negative sign, we use the curled palm right hand rule. Curl the right hand palm along the Amperian loop with fingers in the direction of integration. Then a current in the direction of stretched thumb is assigned positive sign, and the current in the direction opposite to the stretched thumb is assigned negative sign. So in the above figure, for the distribution of currents I1 and I2, they are coming out of the paper because they are shown by a dot in the circle. These two currents are parallel to the stretched thumb, hence these are positive. On the other hand, I3 is going into the plane of the paper because it is shown by a cross mark in the circle. Therefore, it is considered as negative. So, current I is the sum of all these currents in the Amperian loop. Hence, the equation becomes closed integral b cos theta dl equal to mu 0 in bracket I1 plus I2 minus I3. The current I4 is not within the Amperian loop. As the integration is over a full loop, the contribution of I4 to B is cancelled out. From this discussion, let us consider the application of Ampere's law. Let's consider a long straight wire carrying a current I as shown in the figure. B bar and dl bar are tangential to the Amperian loop. Here, the loop is nothing but a circle. Therefore, we can write the equation as b bar dot dl bar equal to b dl. It is equal to b dot r d theta. dl is a small arc on the circle, r is the radius vector, and d theta is the angle at the center of the circle. So by the formula angle equal to arc upon radius, here d theta equal to dl upon r, so dl can be written as r d theta, and hence the equation becomes b dot r d theta. The field B bar at a distance r from infinitely long wire is given by B equal to mu 0 I upon 2 pi r. The magnetic field B of an infinitely long wire is proportional to the current I but inversely proportional to the distance from the wire small r. Therefore, the closed integral over b bar dot dl bar is equal to the integration from 0 to 2 pi, because angle at the center will vary from 0 to 2 pi, mu 0 I upon 2 pi r d theta equal to mu 0 I. This is in agreement with the Ampere's law. If the distribution of currents has a high degree of symmetry, then the magnetic field for the given distribution of currents can be easily calculated. From all above discussion, we can say that the Biot-Savart law plays a role in magnetostatics, same as Coulomb's law plays in electrostatics.
Article we study Ampere's law. Now we'll discuss the application of Ampere's law, that is the magnetic field along the axis of a long straight solenoid and magnetic field along the central axis of a tube of toroid. Let us see first what is solenoid. Solenoid is a cylindrical coil of wire acting as a magnet when carrying electric current. A solenoid is a type of electromagnet, the purpose of which is to generate a controlled magnetic field in a volume of space when an electric current is passed through it. The figure shows schematic diagram of a cross section of a current carrying solenoid. The magnetic field B is parallel to the axis of solenoid. The lines are widely spaced outside the solenoid and hence the magnetic field is weak in this region. For an ideal solenoid of finite length, the magnetic field is uniform and strong at the center and comparatively weak at the outside of the coil.
Let us derive the formula. To apply the Ampere's law, an Amperian loop should be considered. So let us consider an Amperian loop as shown in the figure. By the statement of Ampere law, that is closed integral over b bar dot dl bar equal to mu 0 I. Over the rectangular loop ABCD, the above integral take the form as integration from a to b bar dot dl bar, plus integration from b to c, b bar dot dl bar, plus integration from c to d, b bar dot dl bar, plus integration from d to a, b bar dot dl bar equal to mu 0 I. In this equation, I is the net current encircled by the loop. Now from the diagram, the direction of magnetic field B is perpendicular to the sides BC and AD. So their dot product will be 0. Hence second and fourth integrals are 0. The third integral is 0 because outside the solenoid magnetic field is 0. The side CD of the rectangle is outside the solenoid, hence b equal to 0 and fourth integral also 0. Therefore, the equation becomes integration from a to b bar dot dl bar plus 0 plus 0 plus 0 equal to mu 0 I. Therefore, bl equal to mu 0 I, because b can be written out of the integration sign and integration from a to b dl bar equal to l. Therefore, the equation is bl equal to mu 0 I. If n be the number of turns per unit length of the solenoid and current flowing through the wire is I, then the total current flowing through the path is I equal to NLI. Substituting value of I in the above equation, BL equal to mu 0 NLI small I. L from both the sides will get cancelled and the final equation will be B equal to mu 0 Ni. It is the magnetic field produced by the current flowing through the solenoid. Now let us consider how to obtain magnetic field along the central axis of a toroid. You might have seen a pressurized rubber tube inside the tire of a vehicle. Toroid has the same structure. A toroid is a solenoid of finite length bent into a hollow circular tube-like symmetric structure. It is shown in the figure. Using Ampere's law and considering the symmetry of this structure, we can obtain the magnetic field along the central axis of the tube. We know that to apply Ampere's law, we have to imagine a circular Ampere's loop along the central axis of the tube. So consider the Amperean loop along the central axis. The magnetic field lines are concentric circles in the toroid. The direction of the field is given by the direction of current I in the coil around the toroid. By Ampere's law, the closed integral over B bar dot dl bar equal to mu 0 I, where I is the total current encircled by the loop. Here B can be written outside the integration sign, and integration dl is nothing but L. So the equation becomes BL equal to mu 0 IN. Here total length of the toroid is nothing but the circumference of the circle. It is equal to 2 pi r. So here L can be replaced by 2 pi r, and the equation is B into 2 pi r equal to mu 0 IN, where N is total number of turns in the toroid. Therefore, the final equation is B equal to mu 0 IN upon 2 pi r. This equation gives the magnetic field along the central axis of the toroid. From this equation, B is, that is magnetic field, is inversely proportional to the radius of the toroid. In solenoid, the magnetic field is constant over the cross section, but here in the toroid, magnetic field is not constant over the cross section. So with this discussion, the theory part of this chapter ends over here. In the next lecture, we'll solve few numericals. Before that, you all go through the chapter and collect the formulae, make the list of formulae for the numerical part.